Thank you everyone for being here. Thank you for inviting me to give this presentation. Thank you for the introduction. Dr. Fahad, by the way, is my former PhD student, so we have known each other for many years at this point. I would also like to welcome some visitors who are colleagues of mine from Sultan Qaboos University who came today. And of course, Professor Asghar Kadir. It's an honor to be able to give a talk in front of this audience. So my topic today is fractional complex derivatives and generalizations. So I'm going to be combining ideas from fractional calculus and complex analysis. So this talk is based on several papers and continuing work. So first we have a paper with my first PhD student, Sheima Bouzouina, published in 2021. The second one is with my former master's student, Jihan Gouder, and just very recently graduated PhD student, Wala Yassin, published 2024. Another paper with Wala Yassin, published 2025. This is a short sort of chapter in a proceedings volume with Wala Yassin. Another paper with her, submitted to complex analysis and operator theory just recently. And there's a lot of future directions of this work, which I will show at the end of the talk. I will talk about all of these future ideas and directions. So here's the outline of the talk. I'm going to introduce ideas from fractional calculus and complex analysis and then bring them together. So I'm going to be talking about fractional d-bar derivatives, mostly in the complex plane, Riemann-Liouville type, Caputo type, with various properties. Other related work will include an introduction to quaternion and Clifford analysis, which is a direction in which this work has proceeded more generally. Fractional polyanalyticity is an interesting topic which gets its own section, and then, as I said, ideas from future work. So I guess everyone or almost everyone here probably already knows what fractional calculus is, but I want to briefly discuss the philosophy of this idea in this field. So fractional calculus is about taking the basic operators of calculus and raising them to fractional orders. So a derivative, for example, not only to the nth order for a natural number, but to some nth order where n is not an integer. Now, the obvious question is, how do we define this? How do we make sense of this? We cannot just say, apply the derivative n times. That doesn't make sense if n is not an integer. You cannot apply a derivative operator 1.5 times. It's meaningless. So what we need to do is we need to find an alternative formula for this, which is equivalent for natural numbers and admits an extension, a natural extension to non-integer values. So we need to find some formula which is equal to this when n is an integer and also makes sense when n is not an integer. So the formula that's most commonly used is the so-called Cauchy repeated integral formula. So if you start with a function f, you apply the integral from c to x. So there is a fixed constant of integration. X is a variable on the top. If you apply this integral operator n times, then what you get is exactly this thing with alpha equals n. So an n minus 1 power here, n minus 1 factorial there, and that is equivalent to the nth integral. And this formula is something which does make sense when n is not an integer, unlike integrating n times, which only makes sense for integer n. So this is the definition of the fractional integral. Here we have the fractional order alpha, which must have positive real part in order for this integral to converge. So it's only integrals, it's not derivatives. How do we define fractional derivatives? We've got two alternative definitions here, which are both associated with the same fractional integral. So there's Riemann-Liouville type and Caputo type. With these definitions, we see the nth derivative and the fractional integral both combined together in different orders. Caputo can also be called regularized because you can define it in this way. You start with the function f, you subtract the Taylor polynomial, so you get a regularized function, and then you apply the Riemann-Liouville fractional derivative. That's the same, that's equivalent to the Caputo derivative. N, if alpha is an integer, it's taken to be equal to alpha. In all other cases, it's taken to be the floor of the real part of alpha plus 1. This choice is to make sure that n minus alpha has positive real part, so that this is well defined, unless it's equal to 0, in which case the integral to the order 0 is just the identity operator. So why do we need different operators? Why can we not just figure out which one of these makes the most sense as a fractional derivative operator? If you take an ordinary first order derivative, we know what that is. There's only one definition for it. So why is there not only one definition for fractional derivatives? Well, the different ways of defining a fractional derivative have their advantages and disadvantages. So here, the advantage of Riemann-Liouville is that it is an analytic continuation with respect to alpha. Alpha is now a complex variable defined on the right half plane here. If you extend that to the left half plane, you would get integrals to negative order. Analytic continuation is unique in complex analysis, and the integral to negative order is exactly the derivative to positive order. So we use this convention, and that gives the Riemann-Liouville derivative. So sometimes we use the word differintegral to mean a fractional operator in general. Could be either an integral or a derivative. The Caputo derivative, on the other hand, has the advantage that the Caputo derivative of a constant is always 0, which is somehow what you would expect for any sort of derivative operator. And in fact, the kernel of the operator, as in the space which is mapped to 0 by the operator, is a space of polynomials for the Caputo derivative. Remember this, because we will come back to this later. The kernel of the Caputo derivative is the same as the kernel of the classical repeated derivative. The nth derivative of a polynomial of degree less than n is 0. So the Caputo derivative has a nice kernel, and therefore, if you set up a fractional differential equation of Caputo type, the initial conditions will be nice. They will be of classical type, whereas a Riemann-Liouville type differential equation, the initial conditions would be fractional, which are harder to measure and interpret. So a lot of applied scientists prefer to use Caputo for this reason. I'll show you quickly the fractional differintegrals of a couple of basic functions just to explain why we have this constant c. So c as a constant of integration makes sense. Why do we still need it for derivatives? We don't have a constant of differentiation in classical calculus. The reason why we need it is you could just fix c equals 0 and you get some very nice identities for power functions. This is exactly what you would expect for the fractional integral or derivative of a power function. This is exactly what you would expect for the fractional integral derivative of an exponential function. But that's with c equals minus infinity. And these two things, which are both very nice, they're not consistent. We cannot have both of them. So therefore, if you want to use, for example, something involving Taylor series of functions with power functions, you might want to put c equals 0. If you want to use Fourier series involving exponential functions, you might want to use c equals minus infinity. C equals 0 has a nice connection with Laplace transforms. C equals minus infinity has a nice connection with Fourier transforms. And this is why we cannot just say we fix one value of c that is the most natural, because there is no single value that's most natural. It depends on what you want to do with it. Composition properties are not always what you would expect. So if you take the fractional integral of a fractional integral, you have this nice semi-group relation. It's again a fractional integral. So beta here, they look like derivatives, but beta is negative or real part negative, which means this is actually an integral. That one could be either a derivative or an integral. So differintegral of an integral is a differintegral. Classical derivative of a differintegral is a differintegral. These are the only two cases in general where you have a semi-group property. So if you take a fractional derivative of a fractional derivative, you don't necessarily get just a fractional derivative. You have this extra sum kind of error term involving initial values. So that's the end of my introduction to fractional calculus. I'm now going to pass to complex analysis, and then we'll see how to bring these things together. Now, complex analysis, of course, is a very standard topic. People learn this in bachelor's, but I'm going to make it a bit more interesting. I'm going to show some non-standard things that maybe people didn't learn in bachelor's. Okay, so complex differentiable, we know what this means. Complex derivative exists, holomorphic, analytic. This is equivalent to the Cauchy-Riemann equations on the domain of the function. But this is a very strong condition. So holomorphic functions have so many nice properties that often we want to consider functions that are not necessarily holomorphic. We want to work in some maybe bigger function space with some weaker differentiability properties. So we can define these two complex partial derivatives in terms of the partial derivatives with respect to x and y. Okay, so this is with respect to z, this is with respect to z bar. If your function is holomorphic, analytic, then the z bar derivative is 0, and this partial z derivative is the same as the complex derivative that we already know. In fact, the z bar derivative equals 0 is equivalent to being holomorphic or analytic. So we can, informally, we can think of z and z bar as independent variables. Of course, they're not independent because one is the complex conjugate of the other, but if x and y are independent, then there is a linear transformation. Z and z bar are sort of real independent, even if not complex independent. And this makes sense. So I'll show you a very nice thing that many of you probably have not seen before, an explicit formula for a holomorphic function in terms of its real part. So everybody knows that if you fix the real part of a holomorphic function, so here we have f equals u plus iv. If you fix u, then v is uniquely determined, and f is uniquely determined. We know this. So how would you do it? You could use the Cauchy-Riemann equations, you could differentiate and integrate to find the correct function v. But you can do better than that. We can have an explicit formula with no derivatives or integrals involved, just a substitution. So let me show you how this works. This is not really related to my topic today, but it's just a fun fact that I thought I would include. So you can think of this as f of z and z bar, okay, the two independent variables, where actually we know that it only depends on z. So that means you can set the z bar to be a constant, z naught bar, and leave the z as variable, and this is still the function f of z. And then you get this. So u of x and y, we're using x and y in terms of z and z bar, the simple linear substitution. You can set z to be constant, to be z naught, keep the z bar as a variable, and take the complex conjugate of the whole thing. A little bit of manipulation, and what you come out with, if you compare this last line with the second line, what's inside the u and v parentheses is exactly the same. Z plus z naught bar over 2, z minus z naught bar over 2i, it's the same as this. The only difference is that here you have a plus iv and here you have a minus iv. So if you add these two together, you will cancel the v totally and you will get 2 times u. So this means you can express f of z purely in terms of u. This is going to work for any function u, like a harmonic function, something that is the real part of a holomorphic function, as long as your function f is holomorphic in the neighborhood of z0. So if you have an entire function, a simple choice would be z0 equals 0. You can try this. You can substitute for any holomorphic function. You can check that this works. So it's a really fun formula, explicitly getting f in terms of u. Now going back to these complex partial derivatives, they can also be called Wirtinger derivatives. And they can be combined together. If you combine the z and z bar derivatives, you get the Laplacian up to a constant, which is again a nice fact. You can also raise them to powers, combine them, iterate them, just treat them like partial derivatives basically. D by dz bar is often called the d bar derivative, and this has a bunch of applications. So the d bar derivative is used to define polyanalytic functions, pseudo-analytic functions through differential equations. There is a Pompeiu formula, which is a generalization of Cauchy's integral formula, a sort of Stokes theorem type of thing in a complex setting, which requires d-bar derivatives. The d-bar formalism is a method for solving PDEs, which uses this d-bar derivative, and it also has real applications. So this d-bar formalism can be used to invert the radon transform, which is used in medical imaging, like imaging of the brain. So there are real-world applications of this stuff. I've mentioned a few papers, because there will be a bibliography at the end. Tomography imaging, neural networks, signal processing. This d-bar appears in many fields of science. So we're coming to the end of the introduction. Let's think about how to combine these things together. Fractional derivatives to complex order, this is trivial, right? We already said real part of alpha greater than 0. The order alpha can be a complex variable. Fractional derivatives with respect to a complex variable, not trivial, but classical, already done, going back to the 19th century even. So these things are not going, there's no novelty here. But these are complexifying fractional calculus. So you can think of starting with the operators of fractional calculus, these, and making alpha complex or making x complex. These things are easy, they're already done. What about fractionalizing complex analysis? So for example, taking these operators and making them fractional. That is a different idea. Complexifying fractional calculus is not the same as fractionalizing complex analysis. Can we find fractional versions of the d-bar derivative, complex analyticity, Cauchy's theorem, residue theorem, all these things from complex analysis? And it turns out that this is something that has not much been studied. There's many people working in fractional calculus, but they're not really looking at these things. They're not doing fractional versions of complex analysis. So let's start with the idea of fractional d-bar derivatives. The motivation for this work, by the way, came from the d-bar formalism. So this is something that my PhD supervisor, Dionysius Fokas, he was an expert in this, expert in PDEs, used the d-bar method a lot. So I thought, can we use this to solve fractional PDEs? So let me go and look up, is there a fractional d-bar derivative? Someone must have defined this. But no, nobody had defined it. So I had to ask this question for the first time and go ahead and define a fractional d-bar derivative. So this is the starting point of this research. Can we define fractional powers of these complex partial derivatives, in particular d-bar? So, as I said before, to define a fractional version of anything, we cannot just apply the d-bar derivative a fractional number of times. We need a formula that can be fractionalized. And remember that a fractional derivative is not only interpolating between a function and its derivative. A good fractional derivative should generalize all nth order derivatives, not only 0 and 1. So let's have a look at the nth order or kth order Oettinger derivatives. We raise this d-bar operator or d by dz operator to the power of k, and we can expand this as a binomial sum, right? We have binomial coefficients, we have basically partial derivatives with respect to x and y. So this is like the binomial sum for a plus b or a minus b to the power of k. What happens if k is fractional? What's the binomial sum for a plus b to the power of alpha? Instead of a finite sum, we get an infinite series. And now the reason why I've written two formulae for each of these, so one of them has, basically we're swapping n to be k minus n. These are equivalent, of course. Those are equivalent to each other. But when we make them fractional, we get things that are not equivalent. So equation 1 and equation 3 are both defining alpha derivatives, alpha order with respect to z, but in two different ways. Equation 2 and equation 4 are both fractional d-bar derivatives, but in two different ways. They're not equivalent to each other. They are equivalent if alpha is a positive integer, obviously. That's the nth order d-bar derivative that we started with, but not equivalent in general. We continue to use this convention, which means if you look at the fractional operators appearing here, so the order alpha minus n, when n is large, that's going to be negative. They're almost all fractional integrals. Just the first few terms of the series will be fractional derivatives, and the rest are fractional integrals, which helps when we're thinking about what sort of space this is defined on and so on. So a function space, we came up with this as a sufficient condition. It's probably very possible to improve this assumption. It's not something necessary, but on this space, definitely the operators are defined. This is a Dindray-Coleman type space. We take smooth functions, infinitely real differentiable, not complex differentiable, infinitely real differentiable, such that all of the real derivatives are bounded by some constant b that is uniform, does not depend on n. So on that space, all of these things are well defined. The series are convergent. You can prove some bound, which, yes?
This function f is holomorphic or not?
Not necessarily, no. Because if it's holomorphic, then the classical d-bar derivative would be trivial, would be 0. So looking at these complex partial derivatives is a way to extend beyond just looking at holomorphic functions to a more general class of complex functions. So we need real differentiability just to be able to define these things for all n, these derivatives, but we don't need complex differentiability. That's an important point. So a couple of example functions. Let's see how these new operators work. If we apply them to exponential functions with c equals minus infinity, we know that's the nice choice for exponential functions, then the z derivative has this nice natural formula. The z bar derivative comes to 0. So this is an entire function. Its fractional z bar derivative is equal to 0. It's sort of what we would expect. Okay, we have a nice formula for the z derivative. We have 0 for the z bar derivative. So far, so good. This suggests that our definition is somehow natural. When you take a power function with c equals 0, then suddenly we don't get the expected formula. What you would expect to get would be simply this by itself. for the z derivative, z to the power m minus alpha times this factor. What you would expect for the z bar derivative, again, this is an entire function. You would expect the z bar derivative to be 0, but no, it's not. So this indicates that the new operators are not trivial. They're not always going to give just exactly what you would expect from classical complex analysis. There's something more interesting going on. It also makes sense if we think about in classical fractional calculus, these are Riemann-Liouville type operators, right? So the Riemann-Liouville derivative of a constant is not 0. So the Riemann-Liouville d bar derivative of a holomorphic function is not 0. Kind of makes sense from the fractional calculus viewpoint. Here's another thing that makes sense, which is the fractional Leibniz rule. So actually, I meant to put some slides earlier on about the fractional Leibniz rule in fractional calculus, but I forgot to do that. So basically, we have results like this in classical fractional calculus, just with the Riemann-Liouville derivative. We have this very nice Leibniz rule. So this is again a binomial type series. Okay, you have alpha minus n and n with a binomial coefficient and an infinite sum. This can be generalized to here alpha minus gamma minus n and gamma plus n. So gamma is totally free. It can be anything. You introduce an extra degree of freedom, which is very unexpected, by the way, that you can do that. You still have this freedom of choice of gamma. It can be anything. And from these results, in the classical real setting, we can get the corresponding results for these new fractional complex derivatives. By the way, using this result in the real setting is not enough to prove the corresponding result in the complex setting. We need the more general version. We need the freedom of choice of gamma, because somewhere in the proof there is choosing gamma in such a way to get this nice result. Composition properties, very similar to in classical fractional calculus, which I showed you earlier. If you take the nth derivative of a differintegral, you have a semigroup rule. If you take the differintegral of an integral, so beta negative, then you have a semigroup rule. The semigroup properties are exactly the same as in fractional calculus. In general, we don't have a semigroup rule. Alpha derivative of beta derivative is alpha plus beta derivative minus some complicated expression. It's more complicated this time than in classical fractional calculus. We move from real to complex, we get more complicated. Involved in this expression is a finite sum of binomial coefficients, which I couldn't find any closed form for this. If the thing on the top was just p, then it would be simple, it would have a nice closed form, but the involvement of this q means it's something more difficult. I mean, if anyone knows how to figure out a nice closed form for this, let me know, but so far I've just kept it with a notation like that and put it in the sum as a coefficient. So these are z's, these are z bar, similar formulae, just small differences, but the same sort of shape overall. So, next question is, yes?
So all these expressions involve series, infinite series.
Yeah.
So do they always work? Are these always convergent?
Well, that's why I had to think about function spaces. So if you assume that Dendrich-Kahneman type space, then the things converge. We proved it on this space. But probably other spaces could be used, maybe bigger than this. It's an interesting question to figure out what are the assumptions to make sure these series converge.
So even when you do the manipulation with them, okay, so on the first definition it's converge, but after you introduce some manipulations, for example, you do it for specific functions, you get new terms, so do they still converge?
Yeah, because you kind of have series within series that are all convergent, and it's, I think, locally uniformly convergent, so you can do the manipulation that you need. Yes. Right. So everything we've done so far has been of Riemann-Liouville type. But you remember when I first introduced fractional derivatives, I showed you Riemann-Liouville type and Caputo type. These are sort of not agreeing with each other. So can we define fractional Wertinger derivatives of Caputo type? So let's just go back and have a look at the definition we used for the Riemann-Liouville type. Okay, here are the original definitions, the fractional complex derivatives. So inside these formulae, we have some fractional real derivatives. So one thing you might think about doing would be just replacing these derivatives of Riemann-Liouville type by derivatives of Caputo type, real Caputo derivatives. But we thought about that and realized that that's not going to give us the properties that we want, and that's not really philosophically in line with what we are doing. Because what we are doing here is we're taking a global fractional power, so a fractional power of the whole d-bar operator. We're not doing things kind of term by term. Some other people did this term by term fractionalization, I'll show you later, but what we're doing is taking the whole thing overall. So again, we don't want to look term by term in this series and replace everything by Caputo. We want to have something which has properties like the Caputo derivative, which means we want to do this. So we want to take a fractional integral of a Caputo derivative, of a nth order derivative. That's how we defined the Caputo derivative in fractional calculus. That's how we want to do it here as well. So I'm putting star to indicate Caputo, alpha minus n on the outside, n on the inside, and of course the nth derivative can be expressed simply in this way, the nth power of the first order derivative, and then for this fractional integral we have a series. So these are with respect to z, and then with respect to z bar, of course in a similar way, n is playing the role that it normally is, either equal to alpha or equal to floor of real part of alpha plus 1. Okay, to make sure that this alpha minus n is really a fractional integral. Okay, so these are the Caputo type operators. I should have written somewhere here that we want real part of alpha to be greater than or equal to 0, just like with the original Caputo derivative. So that's an assumption. Now, what about relations between Riemann-Liouville and Caputo? When I introduced the Caputo derivative, I showed you this regularized formula, which is that it has a close relation with Riemann-Liouville. It's equal to Riemann-Liouville minus something. Okay, so here's what we get for our, I think something's gone missing from this slide, but anyway, this is for z bar, and here it was supposed to be for z. So this is the Caputo type, this is the Riemann-Liouville type, and one of them is equal to the other minus this big expression. So again, it's similar to the classical type relation, classical fractional relations, but the sum, the difference that you get is something more complicated, because we've gone from the real case to the complex case. By the way, about series convergence, 2 of these series are finite, so you don't have to worry. It's only this one, and this one comes from the thing that we already proved to be convergent under the suitable conditions. So it turns out in quite a few of these expressions that if there are multiple series, all but one of them are finite sums, which is pretty nice. So analytic functions, we already saw that the fractional d-bar derivative of an analytic function is not always 0. We did this example of z to the power m, where m is a natural number, so it's an entire function. So for Riemann-Liouville type, we can use the Leibniz rule to say f of z is 1 times f of z. And then we take fractional integrals of 1, ordinary derivatives of f of z, but all of the d-bar derivatives of f of z are simply 0. Except for the first one in this sum. So the whole sum collapses to its first term if the function is analytic, and we get simply these formulae. Okay, so that's the Riemann-Liouville type d-bar derivative of an analytic function. What would we expect for the Caputo type derivative of an analytic function? What's the kernel of a Caputo type operator? It's the same as the kernel of the classical derivative. It maps the same functions to 0. Polynomials, constant functions in fractional calculus, right? So, in this complex setting, what does the classical d-bar derivative send to 0? Analytic functions, so therefore, Caputo should also send analytic functions to 0, and it does. So we proved this. This is, of course, in keeping with the philosophy of fractional calculus. So what we have in real fractional calculus, we also have with these new operators. So now I pass through, so you see up here, the sections on Riemann-Liouville and Caputo. Not sure how I'm doing for time. Yeah. So I'm going to go on to hypercomplex analysis. I don't have time, I wish I had time to talk about all the different directions that this work is going in. But what I'm going to do is just give you a brief introduction to hypercomplex analysis, and then kind of summarize what we've done in this direction without going through the details. So basically, hypercomplex analysis is when you take complex analysis and extend this structure, this theory, to higher dimensional settings. For example, the quaternions, bicomplex numbers, Clifford algebras. It's a very interesting field. It's also interdisciplinary. So I know there's some algebraists here. This might be more interesting for you guys. Because Clifford algebras, they're essentially an algebraic structure, but also a geometric structure. So they bring together algebra and geometry, and then you do analysis on this kind of space. So you've got analysis, algebra, and geometry, and it has applications in physics, in different branches of science. So it's really interdisciplinary, and there's a nice research community also in hypercomplex analysis who've kind of taken interest in this work. So what we've done in some of the papers that I mentioned at the beginning of the talk is extended these fractional d-bar derivatives into quaternionic analysis and Clifford analysis, and we're currently working on bicomplex analysis, so many different hypercomplex settings. Let's start with the quaternions. Maybe a lot of people have seen these already. This is a four-dimensional real vector space. So you have x0 plus x1i plus x2j plus x3k. So the basis of the vector space is 1ijk. But it's not only a vector space, it's also an algebra, because you have multiplication rules between these ijk. One is the multiplicative identity. I squared, j squared, k squared, they all square to -1. So somehow they all behave like complex units. They also have relations between themselves, like this. So these are Hamilton's rules of multiplication. William Rowan Hamilton basically created this quaternion set, the theory of quaternions. I believe there is a bridge in Dublin where he kind of graffitied on this set of quaternions when he first came up with the idea. This is a non-commutative algebra. You can see that ij is not the same as ji. And it extends, so this is William Kingdom Clifford, extended this to a more general setting, which is now called Clifford algebra. I think Clifford himself called it a geometric algebra, which indicates how we have both geometry and algebra involved in this topic. So this is, again, a non-commutative associative algebra, and it's built from basic building blocks of Rn plus 1. So Rn plus 1 is called the space of paravectors. A paravector is a combination of a scalar and a vector. So E0 is a scalar, that's basically 1. You see, you multiply by anything, it's a multiplicative identity. So we have 1 for scalars and an n-dimensional vector space. And from these, we add them together, we multiply them together, so we define rules of multiplication. The square of one of these unit vectors is either +1 or -1. That's where the P and Q come in. So P and Q is like the signature. P plus Q equals N. For the first P basis vectors, the square is 1. For the last Q basis vectors, the square is -1. And we have these multiplication rules. Notice EI, EJ is not equal to some EK, as we saw in the quaternions. It's just, this is what we call a bivector. So this is where the geometry comes in. You have vectors which are one-dimensional. It's like giving length a direction. Can you give area a direction? If you have two vectors, you can give a direction to area, like an orientation. And if you have three vectors, you can give a direction to a volume. That's called a trivector. And you create a bigger vector space out of this. So the dimension of CLPQ is going to be 2 to the power of n. And it decomposes into scalars, vectors, bivectors, trivectors, and so on, up to the last thing, which is when you multiply together all of the basis vectors, and that's called a pseudo-scalar. Because in some ways, it sort of operates like a scalar. You've got a one-dimensional space here at the end, like the one-dimensional space of scalars. Not commutative, it is associative. The overall algebra has dimension 2 to the power n. So we started with Rn, with an n-dimensional vector space, n plus 1 dimensional with paravectors, and then 2 to the n dimensional for the overall Clifford algebra. The basis elements are formed by these multivectors, as you can also see here. And the signature is preserved under a change of basis, so that means the definition is well-founded and homogeneous. It does not depend on your choice of basis. You can define this Clifford algebra on Rn without thinking about which are the basis vectors. Examples, real numbers, complex numbers, and quaternions are all some of the basic particular cases of Clifford algebras. So what about analysis? Can we extend the concept of a holomorphic function into a Clifford algebra? So this is what you would think of as a definition of a derivative. That doesn't work anymore. In the quaternions, the only functions that this limit exists are linear functions. So linear functions are too simple. The theory is already well known. There's no point in considering this definition even. In a Clifford algebra, the definition doesn't even make sense because we have zero divisors. We cannot just divide, sorry, we don't have zero divisors, but we don't have inverses. We cannot just divide by something. In the complex numbers, we can divide. In the quaternions, we can divide. But in a general Clifford algebra, we cannot necessarily divide. It's not a field. So we need some other way of defining holomorphicity. We might think about power series. So in complex analysis, you have the analytic Taylor series is equivalent to being holomorphic, complex differentiable. But that's not useful either, because in the quaternion or Clifford setting, it would just give all real analytic functions. No equivalence of the Cauchy-Riemann equations, no really complex or hypercomplex context. It's just real functions on a real vector space, which again, there's no new theory there. So what other equivalent conditions are there in a complex analysis for being holomorphic? We have Cauchy-Riemann equations, we have complex differentiable, we have Taylor series, we have d bar derivative equals 0. And a d bar derivative you can extend to Clifford algebra. So there are different suggestions, by the way. This is not the only way of defining holomorphicity. There are various ideas, but this is, I think, the most common one. So it's applicable to paravector functions. So remember, paravector is scalar and vector. So you differentiate with respect to x0, that's the scalar part, and then with respect to each part, each component of the vector, and you multiply by the corresponding basis element. So in the case of complex analysis, this would simply be dx plus I dy, and dx minus I dy, which is exactly the complex partial derivatives that we saw earlier. So a paravector function is left holomorphic if d bar f equals 0, right holomorphic if f d bar equals 0. Why do we need two different things? What's the difference between these? Well, multiplication is not commutative. So if you apply your operator, which includes these EKs, if you multiply by EK on the left or on the right, that's not going to be the same. So the left holomorphic and right holomorphic functions are not necessarily equivalent. It's not commutative, it's not symmetric, we need these two different definitions. So this means that in complex analysis, the d-bar derivative is nice, but it's not the only way to understand holomorphic functions. In Clifford analysis, the d-bar derivative is even more important. So here I just kind of briefly summarize what we did, because I don't have time to go into all the details, but I do give the references as well. So we defined fractional powers of these d-bar derivatives in both quaternions and Clifford algebra, CL0n. We examined their action on some particular functions. The Fouette polynomial is not exactly a polynomial, but it's like the Clifford version of a polynomial. It involves some symmetric sums of particular types of products. It's an interesting thing that, again, I can't really go into. We also considered, yes?
Say, not polynomial, but these are then, is there a transcendental part to the function?
No, so they are polynomials, but they're not all polynomials. So if you take, for example, the variable x, the Clifford variable, to the power of n, that would be a natural. Yeah, but it's the class that is holomorphic. So if you take x to the power n, that's not holomorphic anymore in this Clifford setting. So you have to sort of modify it somehow. This is, you could say, the Clifford equivalent of polynomials. We also have Clifford equivalent of exponential, trigonometric, and hyperbolic functions, but then we need these so-called radial operators, which is kind of, you consider it in a plane that's called a slice, a two-dimensional plane through the Clifford algebra, which is isomorphic to the complex plane. You have the radial component, the argument component, and you define an operator using that. And we define fractional powers of those things as well, and considered how they act on the relevant special functions. We also proved composition results similar to those that I've shown in this talk in complex analysis. So like in fractional calculus, we have some semigroup properties and then some more complicated things with a big sum involved as well. So these are the two papers where we did all of that stuff. Advances in Applied Clifford Algebras is like the main journal of Clifford algebras. And Clifford analysis. You know, all of the community in that topic basically are editors in this journal. Journal of Mathematical Analysis and Applications is a more general analysis journal that I guess everyone is familiar with. 2024, 2025, This was with my master's student and PhD student at that time, and then I continued with this PhD student, Wala Yassin, with lots of ongoing work, as you will see in the last slides. So I also mentioned briefly a previous definition. So some of these guys from the Clifford community, they defined another type of fractional d-bar derivative. So reducing it to the complex case, just for easier understanding, it would look like this. We discovered this, by the way, after doing our first paper on fractional d-bar in the complex plane, because I didn't know about Clifford analysis at that time. So if you look at this definition, we have a Caputo derivative with respect to x, a Caputo derivative with respect to y. So this is a component-wise fractionalization. And they use this to construct some sort of fractional Clifford analysis, but when you think from the viewpoint of fractional calculus, so these guys are not in fractional calculus, they came from the Clifford community to define this. So when I look at this from the fractional viewpoint, it does not reduce to the nth derivative, except when n equals 1. So you don't get the second order, third order, fourth order d-bar derivatives here. You don't have a semigroup property, you don't have a Leibniz rule, you don't have a lot of nice fractional properties. So what this is, I would say, it's a fractional operator, but it's not a fractional power of the d-bar derivative. Maybe these two can be connected with each other. That could be a nice future project, but if we're considering fractional powers of derivatives, then our definition is more natural and has more nice properties than this one. So now I want to come to polyanalyticity, because here's some really beautiful results that are not fully understood yet. What does it mean for a function to be polyanalytic? Well, analytic, as we know, means that the d-bar derivative is 0, or is equivalent to that. So polyanalytic is a generalization which says that the nth order d-bar derivative is equal to 0. So any analytic function must be polyanalytic to all degrees n. But you also have polyanalytic functions that are not analytic. There is a so-called Almanzi decomposition. This is a complete characterization of polyanalytic functions. Any polyanalytic function can be written as a finite sum of analytic function multiplied by a power of z bar. So it's a nice definition, and you get this complete characterization. So the theory of polyanalytic functions is related closely to the theory of analytic functions, because you have these analytic functions with some fixed multipliers. So when you have something involving the nth derivative, now it's natural to ask what happens if this n is not an integer. If we consider what sort of functions have the fractional d-bar derivative equal to 0, essentially the kernels of the operators. So I'm going to look at Caputo first, because Caputo is very simple in this case. As I mentioned before, in fractional calculus, the kernel of a Caputo type operator should be the same as the kernel of the classical operator. So what do we expect to see for a Caputo fractional polyanalyticity? We expect to see the same thing, just polyanalyticity. And that's what we have. Because if the Caputo derivative is 0, then you take a fractional derivative of both sides, cancel out this integral, and then you get the nth order derivative equals 0, and it's easy to check the reverse implication as well. So, as I say, fractional philosophy means this makes sense. There is no separate concept of Caputo fractional polyanalyticity. What about Riemann-Liouville? Riemann-Liouville derivative equals 0 implies this, which implies that the thing inside the nth derivative here is a polyanalytic function. So this fractional integral of f is polyanalytic. So f is a fractional derivative of this polyanalytic function. So after we've done this, we need to calculate that thing, and we need to check the reverse implication, which is not trivial, by the way. It's not easy to check that this function is indeed fractionally polyanalytic. But finally we did it, so we've got this characterization. Type 1 and type 2, remember we've got this index on the left, two different ways to define the operators. And this is the sort of Almanzi type decomposition that says these fractionally polyanalytic functions can be characterized in this way. The sums are all finite, so we have again a holomorphic analytic function out there, but not just multiplied by z bar to the power k, as in the integer order case. We have this complicated thing. All right, so this is not easy to understand from this slide, what's really going on. So we made some tables to show what these functions are in the first few cases. Like n equals 1, and you've got a single holomorphic function times something. n equals 2, you've got h0 times something plus h1 times something else. So let's characterize what these things are. Here you have basically a fractional power of x minus c. This is type 1, and for type 2 it's very similar but just y instead of x. And then we get that the same fractional power is a multiplier every time. And what's inside the big parentheses is a polynomial in x and y of increasing order. Here it's linear, here it's quadratic. What are the coefficients in this polynomial? We have rational functions of alpha bar, which is n minus alpha. So again, we have polynomials in alpha bar on top and bottom. What's the pattern in these polynomials? That's something we're still trying to figure out. So we get basically a sequence of polynomials. You can have a sequence of coefficients. And actually, we calculated more than this. We put the first few terms into the OEIS, and we found something that matches, but we have to prove that it matches and figure out that this is always true. So it's a very interesting project, because we get this sequence coming out. We want to understand not only what it is, but why it is what it is. So we get some sequence, and then why is it that rather than anything else? Not only to verify it, but also sort of to understand where this comes from. So I think I'm coming to the end of my talk. I'm going to discuss some future directions. So one possibility, as I already mentioned earlier, is to think about different function spaces. So we've got this Dendroy-Kalaman assumption, which is sufficient for the operators to be well defined, but not necessary. Maybe we can find other function spaces which are bigger, where the operators can still be defined, the series converge and everything. Fractional CK extension, Cauchy-Kovalevskaya extension. This is something that is very important in hypercomplex analysis. Again, I didn't have time to talk about this. It relates to the Cauchy-Kovalevskaya theorem, of course, for differential equations, but it's like an extension from basic polynomials to Fuerte polynomials. It does that, for example. It turns simple functions into Clifford functions. Somehow you can think of it like that. So this is a project that we started last year with Wele Yassin, my student, and Paulo Cerejeras and Uwe Kahler, who are like two of the big global experts in this field. Like Uwe Kahler is the president of ISAC and the head of this Clifford research group in the University of Aveiro. So it's nice to be able to work with them on this. We're also extending to other hypercomplex structures. I mentioned already bicomplex. This is ongoing work, and that's probably a direction with a lot of potential, because there's different types of hypercomplex analysis, different structures we could consider. These extensions to hypercomplex settings, so far we've only done a Riemann-Liouville type. We looked at Caputo type only for complex analysis, so that can also be extended to the hypercomplex settings. When discussing this project with my former supervisor, my PhD supervisor some years ago, he had another suggestion that was trying to come at this from the integral point of view instead of the derivative point of view. So instead of generalizing the d-bar derivative, generalize the Pompeiu integral formula. Because that's what we do in fractional calculus. We start with integrals and then we go to derivatives. And there's a few other ideas, like doing a double series instead of a single series. There's a few ideas that, at least in complex analysis, maybe not hypercomplex, might give alternative definitions, or might give the same definition. It will be really exciting, in fact, if we define in a totally different way and they turn out to be equivalent, because that would suggest that the definition is really natural and makes sense. So that's been sort of on the back burner for a few years. At some point we should work on that. Fractional differential equations, pseudo-analyticity, and remember I mentioned the original motivation for all of this was to think about a d-bar method for solving fractional PDEs. So at some point, once we've developed the theory enough, we should get back to that idea and try to solve PDEs using these operators. So here's a list of references. I already gave the references of my papers that this talk is based on earlier on, so I didn't put them here so that I could have just one slide of references. And that's all. Thank you for your attention.
Thank you so much. Nice talk as always. Any questions? Comments?
The comment, no. Comment. First, comment. The quaternion, we did work similar to what you're doing with taking the derivative that which are called the d and d bar operators, and using that is to extend from Lie symmetry analysis to complex Lie symmetry analysis.
Okay.
Arran here is one of the people who worked with that as well, and then the partial differential equation. And what we did then was to try to extend beyond the simple to go into quaternions. As soon as we tried doing that with the derivative operator, we found that you apply the derivative operator to Q and to Q squared. No way to keep it consistent.
Where Q is a quaternion variable, right?
Quaternion and Q squared is the square of the quaternion, and there's no way to keep it consistent. The requirements are inconsistent. Yes, it's an overdetermined system, and that's it.
I think this might relate to your earlier question about the Fuetta polynomials, because Q squared is not anymore a nice polynomial in the quaternion setting. It's not analytic. So you need to define your squared, your quadratic, in a slightly different way. Maybe if you did that, it would be consistent again.
Otherwise, in the simple way that I would want it, that if I take d by dq of q, it should be 1, and d by dq of q squared, it should be 2q. It can't be done.
Right, yeah, they don't work anymore in the same way.
And similarly, what we did, and I don't know, that's where the question will come in, what we did was to split with the complex usually, and then forget all about where it came from, and then split again, as if we didn't know that those were complex. So if I had always been complex, any splitting would still be in the same complex. But now this way, and we've gotten to do it again, this we call iterative splitting, and that gives new results. Is that what you call in bicomplex?
Yeah, so bicomplex is, I think maybe it can be interpreted as the tensor product of the complex plane with itself. Again, it's a four-dimensional real vector space, but you have 1, I, which is a complex unit, j, which is a complex unit, and k, where k squared equals 1, not minus 1. You have 0 divisors, but you have commutativity. I think it sounds very much like what you said.
Yeah, it may be related. It's worth trying to explore the connection if there is, because I think that there should be the same thing seen in a different way in the bicomplex.
Yeah, that would be very interesting.
To see whether that comes out to be the same. And now, do try to look into this. That would be of great interest. So I was interested to see the similarity and the difference. What we're doing is with the symmetry analysis in the usual way. And what you're doing is taking it to the complex derivative rather. So we deal with differential equations which are in the normal way, nth order or whatever, and we're going to the complex differential equation. And when you do that, there will be changes which we may find relevant for our purpose. Also, what we have done may be relevant.
Yeah, I will be very interested to see your papers on this.
It's different looking fields.
Yeah. We should share afterwards some papers and files. Thank you.
Thank you for the insightful talk on the fractional derivative. I would like to inquire in traditional calculus, on the classical calculus, we take the phi as the first derivative for the initial or the conditional bound, the boundary solutions of the values. What if, like, in the fractional derivative, my alpha is 1.1, and how it works for the initial conditions or the boundary conditions?
It depends on which type of fractional derivative. So if you have a Caputo derivative, your initial conditions will be the same sort of thing. So if you have all the conditions at the initial value, it would be like y of 0 and y dash of 0. If you take Riemann-Liouville derivative, then your initial conditions would be fractional. So with 1.1 order derivative, I think it would be something like maybe the integral to order 0.9 and the derivative to order 0.1, something like that. There are fractional initial conditions involved, and one of them is a fractional integral and the rest are fractional derivatives, which makes it again complicated. And you cannot always assume that your functions are continuous or even bounded at the initial value, because if you have a bounded function, then the fractional integral at the initial value has got to be 0. So to have the freedom of choice to have a well-posed problem, sometimes you need a bigger function space which allows singularities. That's why people prefer Caputo, because it has simple initial conditions.
And secondly, can you please help me to interpret the derivative in alpha 1.1?
You mean like physical, geometrical interpretation? Well, this is like the big question of fractional calculus, because obviously it's a natural question to ask and we don't really have a convincing answer. So in terms of geometry, I mean, my explanation for why there is not a convincing answer is as follows. So geometrically, think about the first derivative defines steepness, the second derivative convexity. Okay, these are natural concepts. But what about 1.1, 1.2, 1.3, phi, pi, all the possible uncountably many fractional orders? You cannot have a natural interpretation for all of them because there's uncountably many. So the only way to conceivably find a nice geometric interpretation would be somehow involving something that works for any fractional order, but it's in terms of alpha. It's not a simple thing like steepness, convexity. So there is an old paper on this called Shadows on the Walls, which is the only geometric, like partially convincing geometric interpretation that I'm aware of. Physical interpretations, my favorite convincing application of fractional calculus is in viscoelasticity. So if you have a substance that is between viscous and elastic, then you can model it by fractional orders which are between one integer and the next one. So 1.1, I mean, I don't know enough about the applications to know which way around it is, but if, for example, elastic is 1 and viscous is 2, then 1.1 would be something that's viscoelastic but almost elastic. And
I might just add to say 1.1 and 1.2, etc. are already a problem, but it's still an ordered set. Of course, what we're doing is with the complex.
yeah.
You've gone one dimension away from that as well. It's not an ordered set.
Yeah. So even in the reals,
Everyone is doing the geometry there. You really need to go to the infinite dimensional spaces and see it from that perspective.
Yeah, thank you. That's also a good point. I hope this answers your question somewhat.
Yeah. Any other question? Comment? Yes.
But when we as a mathematician, we generalize things to make the rule that we have previous work like classical derivatives to cover the limitations. Does this new definition cover the limitations like singular in case of Riemann-Liouville derivative and integral, like semi-group properties and other analyses? Does it extend the process?
You mean compared with classical fractional calculus? No, because this is not trying to generalize fractional calculus in that way. It's not trying to cover the limitations. It's trying to make So I mentioned the difference between complexifying fractional calculus and fractionalizing complex analysis. So what you're thinking of would be doing some process starting from fractional calculus to resolve these limitations. What I'm doing is different. I'm starting from complex analysis and making a fractional version, which is different from the original fractional calculus. So it's related and they have a lot of the same properties, but we're not setting out to solve limitations of real fractional calculus because that's not that's not the goal, that's not the direction.
Arran, this first part of your talk, is it about extending the rectangle calculus to fractional derivatives? Is it yours, or you have adopted from someone? Or?
No, that's mine. So right at the very beginning, I showed the list of papers. Basically, all of the fractional stuff here is mine, except for the one slide where I mentioned an alternative definition. So in this paper, we did fractional d-bar Wirtinger derivatives for the first time in the complex setting, Riemann-Liouville. Then this paper took it to quaternions. This paper took it to the Clifford setting. This paper is the complex version. This one is polyanalyticity, but all of them are mine.
There are two interesting things. One is that you can introduce fractional derivatives and integrals over complex domain, which is like somehow useful for signal processing. For example, you consider and rectangle calculus as well. Just consider the mean square error function, a complex variable. It's not holomorphic. It's real variable, a real valued function. So you cannot apply classical theory. So rectangle calculus was actually initiated because of this application, particular application.
Okay.
Some people try to use the same thing for complex valued outputs. For example, there are applications in signal processing where your mean square error is actually not, which has actually the use of complex variables, where, for example, your input variables are complex. Where, for example, the additive noise or medium noise or something like machine error, these things. Now, I tried to find rectangle calculus for fractional derivatives like 5 years ago. I couldn't find anything.
Well, this paper is 4 years ago, so.
Yeah, that's the actual question that was made. So, okay. Did you look at the application somehow of the rectangle calculus?
No, because I don't know enough about applications. So I'm not really qualified to work on this. Like, I don't have the background. But if you want to collaborate from the applications viewpoint and me from the pure viewpoint.
I wrote commentaries on that. It doesn't work very well, so I'll share some details.
Sure, yeah. I mean, I think actually in this paper we maybe didn't use the keyword Wirtinger. So this was actually, I think it appeared online in 2019 or 20, but.
You are calling it d-bar derivative.
Yeah. But then later I learned that this word Wirtinger, or maybe we put Wirtinger in the revision of this paper or something.
I
but
wrote comment articles in 2018, 19 and 20 related to signal processing with fractional derivatives.
Okay.
It's, hypothetically, 100% of the articles on fractional calculus in signal processing are incorrect. 100%.
A lot of papers in fractional calculus are incorrect. So.
100%.
So, I mean, do you think that this approach might give a way to do more correct articles in this?
It can at least provide correct mathematical formulation for that approach.
Okay, nice.
Because so far it's heuristic, it's incorrect. Not actually incorrect, it's really like smelling bad.
Yeah.
At least this will give proper mathematical formulation.
Okay, good.
I doubt that it will provide better results,
but at least a foundation.
Correct mathematics.
Thank you.
Any other questions or comments?
Can you tell us a little bit about the function space that you use on which these series converge?
This dendritic element. Sorry, what was the question?
Function space on which you define.
But what about the functions? Just to show it again.
Yeah, just tell us about that. Because it's not a very common function space. It's very restrictive in some sense.
So we came up with it because we need the real derivatives to exist, because we've got n and n is going up to infinity. So it needs to be smooth. in the real setting, infinitely differentiable. And then we need basically a bound on this. If you bound the function and the derivatives of the function, it's enough, because the fractional integral, you know, the first finitely many terms are fractional derivatives, and after that, the tail of the series, they're all fractional integrals. Fractional integral is a bounded operator. So for convergence, it's enough basically to say that these things that we're applying the fractional integral to are bounded, and the bound is always the same. Then you apply the fractional integrals, and then you will get the convergence. So that's how we came up with this, to say that the derivatives are bounded and the bound is always the same. So that is sufficient, but I'm very open to finding other, maybe better function spaces. This is just what we came up with to show, okay, the theory is not trivial, but we don't necessarily have to work in that space.
Does this have maybe some relation to classical function spaces like Sobolev spaces?
Well, again, this is a keyword that did not appear in the original paper. So I discovered later that this is a particular case of what are called Dendrich-Coleman type spaces. And there's a few nice papers about that. I'm not sure what the connections are with other spaces, because I haven't really studied those papers fully yet. But there is an existing theory of those spaces, let's say. So if you look in those papers, that might answer your question. They're used to define a sort of so-called quasi-analytic functions that sits between complex differentiable and infinitely real differentiable. So that could be something useful in complex analysis. It also connects apparently with algebra, because the first paper I found about these, the title is on quasi-analytic local rings. So they're considering germs of functions, and yeah, it's between different topics of maths, but I haven't read it fully yet.
Can you give an example of germs of a function?
Of what?
Germs of a function.
No, I mean, as I say, I haven't really studied that paper properly. I've looked more at the later papers where they're not considering germs, but they're just looking at, you know, smooth functions like this. So the germ stuff I haven't really studied germs of functions myself since my bachelor's in differential geometry, so I can't say much about it, sorry.
And one more question. At the beginning you said that you are going to, this extension will help to solve fractional PDEs.
I hope.
I hope, okay.
Yeah, that was the motivation. I wanted to solve fractional PDEs. I realized this theory would be needed, so now I'm developing this theory. At some point, I need to come back to those fractional PDEs, but it hasn't happened yet.
So that would be a future thing.
Yeah.
Might.
Yeah.
Which type of PDEs?
I'm not sure yet. I mean, in the non-fractional setting, it's been used for PDEs involved with inverting transforms, like Radon transform and so on. But I'm not even sure of its full applicability in the non-fractional setting. So that needs to be studied, and then to figure out how to fractionalize it. It's going to be a big project. That's why it hasn't started yet.
Thank you. Just a stupid question. So in all these formulas, you have a 2 to the power minus alpha term, right?
Yeah.
So I'm not sure if it, even if it makes sense or not, but asymptotically this makes me worried in the infinite. If you, for example, look far enough, I mean, it's getting multiplied with a series.
But what do you mean, like alpha going to infinity, or for a fixed alpha?
Yes.
But alpha is fixed, so alpha is just a fractional order. So if you consider some asymptotics of alpha going to infinity, then maybe it would have problems, or maybe, yeah, I'm not sure about that. But we define these operators just for a fixed alpha, and that, of course, comes from there's a factor of 1/2 outside there, so that's why there's a 2 to the power minus alpha.
All right, I think let's thank the speaker once again.
Thank you.